Hello students, welcome back. Let us resume our discussion in section 6. We went through some motivating examples and then we utilized Hensel's theorems to get through with these examples. And then even more complicated examples with multiple prime factors can be decomposed and then later combined using the Chinese remainder theorem. We went through all those. What we left out is the proof of Hensel's theorem. Let's go ahead and do that, but there's no way I can do it in a single video. Maybe 2, maybe even 3. Let's try. The first preparation is not too bad. This is just a Taylor series expansion. Is everybody comfortable with this? I hope so. In calculus, we had been doing this. Oops. Maybe not exactly. In calculus, we used to use this. F of x, and then here, x minus c to the k power. That's what we used to do in calculus. Maybe one more. Yeah, there you go. That's what we used to do in calculus. But this is polynomial we are dealing with, so there's no need to go to infinite series. Degree of polynomial is n, then after nth derivative, everything goes to 0, so we don't need infinite series. Just finite series will do. And then here, let's take a small change of variable. Let's see if we express it in t. And then let's rename x as t minus c, so that t is c plus x. Then this entire thing becomes, let's see, this is c plus x. And this one here, t minus c, is just x. And that's what we have here. In short, this expression here is nothing new, nothing fancy. It's just Taylor series, Taylor polynomial, something we already know. The punchline of this lemma is the next line. If we begin from the polynomials with integer coefficients, then each Taylor coefficient is also a polynomial expression of c with integer coefficients. You see, this looks like a rational expression. We have k factorial in denominator. But what this theorem says is, in the end, we have a nice cancellation, and we must come down to a polynomial expression of c with integer coefficients if we start from polynomials with integer coefficients. Well, we are dealing with number theory, so we want to stay within integers, so it makes a lot of sense to go through with integers. So let's go ahead and prove it. How do we prove it? Well, we used binomial theorem. Select a polynomial like this, okay, all right, and then replace x by c plus x, and then we have this expression, c plus x to the I power, where I is going from 0 to n. And then we can apply binomial theorem to each of those, like this, as I'm highlighting in blue. Now what do you have? Bunch of ai, which is on integers, and then I choose j, that too is an integer because I is greater than or equal to j, and c to the I minus j power, we have c to the whole number power. So if you multiply appropriately and adding those up, depending upon x to the k power, you have to have a polynomial expression of c with integer coefficient. That's the idea. More precisely, you're going to end up with this particular polynomial expression, but I don't think that's necessary. So we have to have polynomial expression of c with integer coefficient. So if c is also an integer, then we have integer polynomial again. So it may look like k factorial in denominator, but we have to have cancellation. All right, that's the first preparation. Next, Hensel's lemma, which is actually a big theorem, but Hensel named it as lemma. So let's follow that. P is a prime and k is greater than or equal to 2. Actually, this is not really necessary. Greater than or equal to 1 is enough, but that's actually a trivial case. F of x is a polynomial with integer coefficient, and R is a solution of this congruence. F of x is congruent to 0 modulo p to the k minus 1 power. Then the solution of the next generation, f of x is congruent to 0 modulo p to the k power, are as follows, blah, blah, blah. which I'll show you a bit shortly. So basically, this lemma is used for reducing the solutions f of x is congruent to 0 modulo pk into the previous generation, f of x is congruent to 0 modulo p to the k minus 1 power. Here is a bit more formal and simple expression of the condition. P is a prime number, yeah, and double stroke capital P means that of all prime numbers. And k is a positive integer, which starts from 1, not 2, but that's okay. It works for k equals to 1 as well. It's just a trivial case. So trivial that it's stupid, so people begin with 2 many times, but it works for 1 as well. So why not here? It's more general after all. F of x is a polynomial with integer coefficient. By the way, this bracket x means it's a polynomial, and z, yes, coefficients are coming from z. And finally, f of r is congruent to 0 modulo p to the k minus 1 power, yeah, solution of that. So all the conditions are there. And as for the conclusion, well, pay attention here, this is going to be complicated. We have 3 cases. Case 1, sorry about that, this is a typo. I thought I corrected it, but I neglected it. Sorry. F prime of r, where f prime is of course a derivative, f prime of r is not 0, not congruent to 0 mod p, then its multiplicative inverse exists modulo p, so that f of r plus t times p to the k minus 1 power is congruent to 0 modulo p to the k power. You see, in modulo p to the k minus 1 power, in modulo this thing is 0. So any t times 0 is 0. So this thing is just adding 0, so it's meaningless. Modulo p to the k minus 1 power, this addition is meaningless. Adding 0 will not change anything. Modulo p to the k power is not 0, so it is serious. But in this particular case, when t is congruent to negative of fr over p to the k minus 1 times f prime of r to the negative first power, in that particular case, it works out so that we have congruence 0. So we have the solution of this congruence, and not only that, the existence is unique. So we have unique solution. That's case 1. Now case 2, well, we considered when the derivative is 0. How about we consider the case where the derivative is non-zero? Now how about the derivative is 0? Okay, in that case, we subdivide even further. F of r is congruent to 0. In that case, there are multiple solutions like this. It works for all t, so multiple solutions. And then the derivative is 0, and then f of r is non-zero, then there's no solution. Now, did I leave out anything? I didn't. I covered everything. F prime of r is either 0 or non-zero. Non-zero case done. 0 case we have here. And f of r is either 0 or non-zero. 0 case here, non-zero case here. So I covered everything. So the classification is complete. Either we have A, B, or C. In case of A, we have unique solution. In case B, we have multiple solution. Case C, we have no solution. One more thing. This unique solution does not mean absolutely unique solution. And this no solution does not mean absolutely no solution. Because R is a solution of this, but there may be another solution, say S. With respect to S, we may have to do another of those. So even with this, there may be another solution coming from S. With this, there may be some solutions that are coming from S, which is different from R. So, okay, see how this uniqueness is going on? Uniqueness is bounded within R. Okay, all right. The main case is part A. Let's try to prove it. I hope I can complete it in this video. If I can't, then I'll just resume it in the next video. From Taylor's theorem, we have this expansion here. No problem, this is Taylor's theorem. And then please make this observation. Quadratic go higher, they all disappear. We saw that earlier in the motivating example, you remember that? quadratic or higher, all these, as a matter of fact, just disappear. All these just disappear. The reason? P to the k power divide all these because P to the k minus 1 times 2 is bigger than k, and etc. etc. So only the linear term and the constant term matter. Everything else just disappear. We already saw that in the motivating example for exactly the same reason. As a matter of fact, it's coming back again. Okay, now therefore, this thing is congruent to 0 modulo p to the k power. So this thing is congruent to this one, modulo p to the k power. So this minus that is congruent to 0 modulo p to the k power, all right? So actually, excuse me, I neglected one thing. It's a bit harder than that. Sorry about that. Let's go back to this. We got up to here. And then we're going to use this one here, which I am highlighting in red. So it's a bit harder. It's not that trivial. So here, this thing is congruent to 0 means flipping f of r to the other side. F prime of r p to the k minus 1 times t is congruent to negative of f of r here. And then I'm gonna flip these over to the other side to get this red. That's what I'm gonna do. First, let me divide by p to the k minus 1 power. If I do that, divide by p to the k minus 1 power, divide also p to the k minus 1 power, so we get mod p. Does it make sense? We have done it several times. So what do you mean by, no, not this one. Let's see. Okay, all right. Divide by p to the k minus 1 power so that we get this division. Why is it true? Well, basically, it's coming like this. P to the k power divides the difference. So this thing is some quotient q times p to the k power, and divide each by p to the k minus 1 power. Then this one goes away, and then this one becomes just qp, and f of r over p to the k minus 1 power. That's what I'm going to get. And also, going all the way back to the original condition here, which I just highlighted in green, f of r is congruent to 0 modulo p to the k minus 1 power. So p to the k minus 1 power divides r. So f of r over p to the k minus 1 power is a certain integer. So here we have this thing plus this integer is q times p. So that thing and that integer, negative of that integer, is congruent modulo p. So it's tricky, but it works out. And then if I flip over this f prime of r inverse, because inverse exists, because this condition, then finally we get the answer. This thing is indeed 0. That proves the first case. And we're going to resume and prove the rest.